Amongst all the geometrical objects that exist in God's universe, the right triangles are perhaps some of the most interesting. Well, now we know that all right triangles must obey the Pythagorean theorem, but the question is, do we always have to calculate with the Pythagorean theorem in order to know the sides of a right triangle? Well, believe it or not, there are some triangles, right triangles, that exist where special patterns emerge, patterns unique and worth knowing. But in order to study these patterns, we've got to catch ourselves a right triangle first.
All personnel stand clear. All personnel stand clear. All personnel stand clear. All personnel stand clear. All clear. Proceed with caution.
Now yes, we could use the Pythagorean theorem each time to find the side lengths, but after today's lesson, we hope you'll see the advantage of knowing these patterns, and that they only exist with the special right triangles. This is lesson 5.8, special right triangles. Let's go ahead and go to the warm-up. Go ahead and pause the video now. For number 1, the answer is 10. This comes from the Pythagorean theorem in lesson 5.7. For number 2, vertical angles. For number 3, the converse of the alternate exterior angles theorem. Our vocabulary for this lesson is 3, 4, 5 right triangle, 30, 60, 90 triangle, and 45, 45, 90 triangle. Also, the word ratio. Our objective is simple. We want to justify and apply the patterns of the special right triangles. Here's the motivation. You have a steel cable. You know it's 11.5 feet in length. It needs to be securely attached to an unstable wall. And the cable needs to have no slack in it, which means it needs to be perfectly tight. You know that the distance from the house has to be 3/4 the height of the cable from the ground. How far away from the house and how far high in the air should the cable be? Well, after this lesson, hopefully this problem should be very simple to solve. What we have here is a special right triangle. The ratio of the ground length to the height is 3/4. Therefore, we know what we have is a 3, 4, 5 triangle. That's in today's lesson. All we need to do is divide 11.5 by 5, and we're going to get a factor of 2.3. To get the other sides, we only need to multiply 3 and 4 by 2.3, and we're going to get 6.9 feet and 9.2 feet. Those are the missing measures that we need. If we test 6.9, 9.2, and 11.5, we will see that the Pythagorean theorem still works. All right, let's consider a very basic geometrical object. Let's consider a square. Now, since it's a square, all the sides are the same, so we'll call them x. Do you know how to create a right triangle from a square? One of the easiest ways is to simply draw a diagonal. Now we have a right triangle. On top of that, it's isosceles. Two of the legs are the same. Whenever this happens, you have a special triangle called a 45-45-90. Now, all right triangles must obey the Pythagorean theorem. So x squared plus x squared must be c squared. Well, using the rules of algebra, that means that 2x squared must equal c squared. Solving for c and taking the square root of both sides means that the hypotenuse, c, must be x times the square root of 2. This is a 45-45-90 triangle. This is the first kind of triangle that we deal with. Here are some facts. Now, these are always true when you're talking about a 45-45-90. First, it's always isosceles. Two legs will be exactly the same. The ratio of leg to leg must be 1, since x over x must be 1. The ratio of hypotenuse to leg must be the square root of 2. And the ratio of leg to hypotenuse must be 1 over the square root of 2. Now, some students are still confused about ratios. Find the ratio of x to y and then y to x. Well, in the first one, x comes before y. We read it as x to y. That means that x is the numerator and y is the denominator. In the second one, y comes before x when we read y to x. That means that y is in the numerator and x is in the denominator. Here's another right triangle. It's a 45-45-90. It's isosceles. I know it has to be a 45-45-90 without even saying it's 45-45-90 because it's a right triangle and it's isosceles. So there's no choice. It has to be a 45-45-90. Now I know one of the sides is 7. Immediately, that means the other side has to be 7. Now what I do is I use the ratio from the previous slide. I know that hypotenuse over leg in this kind of a triangle is the square root of 2. That means if I let the hypotenuse be c, that c over 7 is the square root of 2. Cross multiplying means that c, the hypotenuse, is 7 square roots of 2. And now the triangle is solved. I know all of the sides and I know all of the angles. Let's use some ratios. This time I know the hypotenuse is 8, but I don't know the sides. Yet I know they're the same, so therefore it has to be a 45-45-90. I'll call one of the sides x. Now I know from my ratios that when I'm talking about a 45-45-90, the leg divided by the hypotenuse must be 1 over the square root of 2. That's an equation that's always true for 45-45-90 right triangles. So that means that x over 8 must equal 1 over the square root of 2. Now I cross multiply. That means that x must equal 8 over the square root of 2. And that is the correct answer. But in geometry and in Algebra 1 and many times in Algebra 2, we don't leave it in this form. It's mathematically taboo in some circles, even though it's no longer historically necessary, like it used to be, to get rid of the square root in the denominator. But that's what we have to do. It's more of a historical reason. Historically, we're talking about years where people didn't have calculators, okay? Well, we have calculators now, so we can calculate this rather easily. But prior to the calculator, it was very difficult to calculate 8 divided by the square root of 2. So what they would have to do is they would have to rationalize. And what that means is that we have to get rid of the square root from the denominator. Now, the way that we do that, and the way that I need to teach you how to do that, because this will be an expectation of you, is we multiply the top and the bottom, the numerator and the denominator, by the square root of 2. That's called rationalizing. Now, the square root of 2 over the square root of 2 is 1. And you already know that when you multiply a number by 1, it doesn't change the number. So we're not really changing the value of this. Well, I multiply the numerator and I get 8 square roots of 2. I multiply the denominator and I get 2. 8 divided by 2 is 4, so my final answer is 4 square roots of 2. Now, even though I'm not going to do it in this slide, if you want to pause the video and then just take your calculator real quick. Take 8 divided by the square root of 2 first, and then do 4 times the square root of 2, and you'll get the exact same number. So 8 divided by the square root of 2 really is the same value as 4 square roots of 2. It just has a different form. It's called simplest radical form. So now I know the legs, and the legs are 4 square roots of 2.
1.414213523730985048
The square root of 2, what is it? Well, it's a number. That's it. That's all it is. And it's a number that many algebra students haven't really worked with very much, which is unfortunate. So let's go back and let's remember what an irrational number is. First of all, square root of 2 belongs to the irrational numbers. And that means that its decimal part repeats forever. But that's not the only thing. The other feature that this number has is that there's no pattern. No matter how many digits you memorize, you'll never have all the digits memorized. There's always some new digit popping up in a place that didn't pop up in the same place before. So it's an infinite decimal value that also has no pattern to it. The square root of 2 belongs to the irrational numbers. So does another number that we're going to use in this lesson. The square root of 3 belongs to the irrational numbers, and we're going to be using that also quite frequently. Now, whether you have a TI-84 or not, plug the square root of 2 in your calculator, and you should get about 1.414213562. Plug 1 divided by the square root of 2 in your calculator, and you should get about 0.707-106-7812. The reason why I wanted to go over this is because many times algebra students haven't worked enough with the square root of 2. And so to them, they don't really see it as if it was a number. And it is. It's just a number. It's just a number that you haven't frequently worked with until now. The next one on our list is called a 30, 60, 90. Now this one's different in several ways. Well, first of all, the angles are different, 30, 60, and 90. But there's another way. It's not isosceles, which means one leg is shorter than the other leg. So what we have here is we have a short leg, a long leg, and a hypotenuse. Now remember, when I say long leg, I don't mean longest leg. The hypotenuse will always be the longest leg in a right triangle. This is the pattern. I'm going to call the short leg x. The long leg is x square roots of 3, and the hypotenuse will be 2x. Now, what if I wanted to order all the sides from least to greatest? Well, it would look like this. The smallest side would be x. The middle side, which we'll call the long leg, will be x square roots of 3. And the hypotenuse would be 2x. So that's ordering from smallest to largest. Let's talk about the ratios. When you're dealing with a 30, 60, 90, the short leg over the hypotenuse will always be 1/2. The long leg divided by the hypotenuse will always be square root of 3 over 2. The long leg divided by the short leg will always be the square root of 3. Again, when I say long leg, I don't mean longest. All I mean is it's the leg that's longer than the short leg. The hypotenuse still remains the longest side. All right, let's go ahead and find x and y. Which side here do I know? Do I know the shortest, the long leg, or the hypotenuse? If you said the long leg, you're correct. So if I ordered the sides, it would look like this. X is the smallest, 5 square roots of 3 is the next one, y is the largest. Now I use this fact. The long leg divided by the hypotenuse will always be the square root of 3 over 2. This means that 5 square roots of 3 divided by y will equal the square root of 3 over 2. The rules of algebra say I can divide out the common factor of square root of 3. This now gives me the equation 5 over y is equal to 1/2. Now I'm going to cross multiply. Y is 10. Next I use this fact. The short leg divided by the hypotenuse will always be 1/2. This means that x over y must equal 1/2. But I know y. Y is 10. So x over 10 is 1/2. Now I cross multiply. X is 5. And now I know all of the sides of the right triangle. Let's do this again. This time I have the hypotenuse, 6 square roots of 2. I order the sides. The shortest is x, the middle side, the long leg, is y, and the hypotenuse, which is the largest, is 6 square roots of 2. Now, I use this fact. The short leg divided by the hypotenuse is always equal to 1 over 2. This means that x over the 6 square roots of 2 is equal to 1/2. Now I cross multiply. 2x equals 6 square roots of 2. Divide both sides by 2. X equals 3 square roots of 2. Now let's use this fact. The long leg divided by the short leg will be the square root of 3. This means that y divided by 3 square roots of 2 is equal to the square root of 3. Cross multiply. This means that y is 3 square roots of 6. Do these three numbers obey the Pythagorean theorem? Well, they should. It's a right triangle, and all right triangles must obey the Pythagorean theorem. That's a fact. So let's try it. 3 square roots of 2 squared plus 3 square roots of 6 squared equals 6 square roots of 2 squared. Now, if you haven't worked with squaring roots very much, let me show you a trick. I already know 3 squared. See, 3 squared is 9. So all I really have to do now is write 9 times 2 without the radical. The radical vanishes. The next one is 9 times 6 without the radical equals 36. Well, where did that come from? Well, that's what 6 squared is. 6 squared is 36. Drop the radical, and now let's multiply. I get 18 plus 54, and that's 72. My final answer is 72 equals 72. So yes, the Pythagorean theorem still works. In order to use the Pythagorean theorem, you have to know 2 of the sides in order to find the third side. And what one of the really cool parts of this lesson is, and really one of the big pictures here, is that if you know the patterns for 30, 60, 90 triangles, then instead of 2 sides, you only need to know 1 to find the other 2. And that makes you more powerful as a student of mathematics. Okay, a lot of students haven't really rationalized very much at this point, and that's unfortunate. So I'm going to make one quick point about rationalizing. It's very easy to do. Doesn't take very much. It's easy to do with square roots. So let's consider the following ratio, a divided by the square root of b. In order to rationalize it successfully, I multiply the top and the bottom by the square root of b. This is the same as multiplying by 1. My final answer will be a square roots of b over b. The whole concept is that the radical no longer exists in the denominator. That's why we rationalize. Another thing that students really haven't worked with very much at this point is multiplying radicals together. This is also very easy to do. Let's say I had a square roots of b times c square roots of d. Well, all I have to do is multiply the outer parts together and the inner parts. So my answer is ac times the square root of bd. Let's look at an example. Here's 2 square roots of 3 times 4 square roots of 6. Well, 2 and 4 are the outer parts. So 2 times 4 is 8. 3 and 6 are the inner parts, so that's 18. Now 8 square roots of 18 is the correct answer. The problem is it's not in simplified or simplest radical form. So what I do is I break up 18 into 9 and 2. Now the laws of algebra, or the rules of algebra, say that 8 square roots of 18 can be written as 8 square roots of 9 times the square root of 2. Well, the square root of 9 is easy. That's 3. 8 times 3 is 24. And so 24 square roots of 2 would be simplest radical form. The last kind of special triangle I want to talk about is a 3, 4, 5. It has nothing to do with the angles, it's all about the sides. This is what a 3, 4, 5 looks like. 3x, 4x, 5x, where x is some factor that they all have in common. Here's the fact that I have. Here's a ratio equation that's true. The short leg divided by the long leg will always be 3/4. As a decimal, that's 0.75. The long leg divided by the short leg will be 4/3. As a decimal, that's 1.3 repeating. The short leg divided by the hypotenuse will always be 3/5. As a decimal, that's 0.6. The long leg divided by the hypotenuse will be 4/5, and that's equal to 0.8. You want the shortest side of a 3, 4, 5 triangle to be 9.5 feet. How long are the other sides? All we need to do here is find the common factor. Since 9.5 is the shortest side, we're going to divide it by 3, which is part of the 3, 4, 5. When I do it, I get 3.16 repeating, which means that number is the common factor. So now all I have to do is multiply 4 and 5 by that common factor. 3.16 repeating times 4 is 12.6 repeating. 3.16 repeating times 5 is 15.83 repeating. Well, this is a real-world problem because this deals with feet, so we don't really have decimals that go forever. So what I do is I round to the nearest hundredth, which is the second decimal place. So that means the sides of the triangle are roughly 9.5 feet, 12.67 feet, and 15.83 feet. Really, the whole point of this lesson is to master this ratio chart. You've got 3 different kinds of special right triangles. You've got 45, 45, 90, 30, 60, 90, and 3, 4, 5. So if you want to write down this chart and basically memorize this chart, you will be a long way off to mastering this whole lesson. All right, here's the lesson quiz. Go ahead and pause the video now. Number 1, 8 square roots of 3 over 3 inches. 16 square roots of 3 over 3 inches. Number 2, 8 square roots of 2 inches. Number 3, y is 3.5 inches, and x is 3.5 square roots of 3 inches, which is approximately 6.06 inches. Number 4, a is 6.6 feet, and b is 8.8 feet.
I'm the Pythagorean theorem. All right triangles must bow to me.
Bit of a snob, that one.
Yeah, you're right.
Oh, I'm going home.
What? What's wrong? Is it something I said? You're a right triangle, man. Come on, you're always right.
Oh, bother. Leave me alone.